Now let's get excited for this next talk, where Stan's going to be talking about PIXIE. Stan, take it away.
All right, thank you. Let me just adjust this. Yep, there we go. So yes, just quick clarification. This is PIXIE with an E, not the package manager. I had a couple of questions about that. Just, you know, we had no idea about the name collision, but anyway, it's technically spelled differently. So yeah, so I'm excited to talk to you a bit today about blending just-in-time and ahead-of-time compilation for scientific Python applications. I am presenting this, but the majority of all of this work was done by Stuart Archibald, one of the Numba maintainers. But yeah, so I'm excited to talk to you about it. I, however, need to preface with a warning that what you are seeing in this talk is very alpha stage code. The code and docs are real. You can go check them out. Go to numba/PIXIE on GitHub. It's all there. So there's no magic here, but it's coming together real fast. The demos work. There are definitely some sharp edges. Things are evolving and improving quickly. However, we've been thinking about this for a long time, so I will say the ideas are in the beta stage. Stuart proposed what turned into PIXIE about 2 years ago, and it's just taken a little while to sort of get going on it and build it out. A lot of complicated problems to solve. But let me set the stage. This is not a talk about Numba. I usually come here and talk about Numba. I'm not actually going to talk about Numba too much in this talk. But Numba is the motivation for this. In case you're not familiar, Numba is a just-in-time Python function compiler for numerical and numerical adjacent use cases, used by, so claims GitHub, tens of thousands of projects. That's awesome. And the idea is it lets you distribute pure Python because it's a just-in-time compiler. Your end user gets machine code speeds. That's all great. Several years ago, we started to think about, after a decade of experience with Numba, how we would evolve the system to address limitations in the architecture, make things more modular. One of the things that we really believe is that there isn't just going to be one compiler for Python. There are going to be a family of compiler technologies. And so we would like to reuse components as much as possible. And so we, in some sense, want to dissolve and reform Numba over time. But of course, we're still maintaining improving current Numba, of course. Don't panic. This is part of the reason this took so long, is keeping current Numba going does take a lot of time. One of the things that we faced in that sort of rethinking Numba is just-in-time compilation is great. We're big fans. There are scenarios where you want to have time compilation. I'll talk about that in this talk. Shouldn't those be built out of the same components? Can you make ahead of time and just-in-time work together? And the more we thought about it, the developer and user experience, we realized that there were some real conflicts inherent in the ahead of time, just-in-time compilation. And so we wanted to figure out how to fix that in some way, to make it so that you didn't have to give up something to go one way or the other. And so we built a component to help solve this problem. That's PIXIE that we're talking about today. This is sort of its big unveiling. We haven't really talked about it in public much. But first, when we reached that impasse of how do we handle ahead of time and just-in-time compilation, we had to go back to what's the point? Why are we doing this? And so, since I like aphorisms, I started with performance needs specialization, which requires context. I repeat this to myself repeatedly when I'm not sure what to do. Frequently, you can see this in the reverse, actually. It's really hard to speed something up if you have to be totally generic and you have no idea what it's being used for. That's often you see it in the negative. And so what that comes to is that the point of compilation is to be able to specialize code with some context. In this case, often the context is, I know what data types are being used, I know the other functions you're calling. You're calling this function that calls that function that calls that function. And so what are you trying to do is kind of the question you're asking up here. And then the compiler can take that with your code and some knowledge of the execution environment. Where are you going to run this? Are you going to run this on an Intel CPU? Which Intel CPU? Intel CPUs keep changing their instructions. You might actually want, you know, the newer vector instructions, but maybe your laptop's old, so you want the older ones. You have to make those sorts of choices. Do you go on a GPU, other accelerators, all of that? And so the compiler can do magic things, but it really needs some of this context in order to work. Which gets us to where the sort of crux of the conflict is that ahead of time and just-in-time compilation feel like sort of two buckets that from the very beginning of writing your program, you have to pick a side. You have to say, where am I sitting? Am I going to do ahead of time compilation and get all of its benefits and then all of its drawbacks? Or am I going to do just-in-time compilation and get its benefits and drawbacks? Excuse me. On the ahead of time side, as was mentioned in the LPython talk, you get really quick startup. You don't have to do a lot of the work that you have to do in a just-in-time compiler. And you have more time for optimization because you do all the optimization at build time, not runtime. You can spend a lot of time doing some really impressive optimizations. If you've seen some compilers where you turn on all the optimizations, especially on like GPU compilers, they can do amazing things. It takes a little while. So you don't want to keep doing that over and over again. But you have some disadvantages. You have to make some choices. You have to pick the architecture you're going to implement. Am I implementing for a generic CPU or a specific CPU? What if the user doesn't have that CPU? And then the other thing is that you can sometimes, although things like LTO help, you can sometimes lose some of the high-level context that would allow you to do cross-module optimization. And so that's in contrast to the JIT side of the equation. When you use a JIT, you have complete context available if you want. You can inspect the entire program. You even have more context. You can actually see the data that's running around in the program. This is something the compiler generally doesn't get to see. It doesn't know if you're processing big arrays or small arrays or anything like that, but a JIT can figure that out. So that's really exciting. You have more optimization possibilities. However, the curse is that you have to do all those optimizations at runtime while the user is waiting. And so you have to worry about either you have a very high latency startup, or you have a warm-up time, or you have any number of other things that make people turn away from JITs and want to go back to the AOT. I mean, if you're going to start a job on a 1,000-node cluster, do you want to compile your code 1,000 times as it starts up? Maybe that's not bad in wall clock time, but that does waste CPU time. And so the other thing is that JIT's not always allowed. There are definitely security situations in which just-in-time compilation is not desirable because you can't inspect the binary ahead of time with maybe some security tools. Certainly, iOS does not allow you to JIT unless you're Apple on your iPhone. And so that's one environment where you are not allowed to JIT. And really, the tension between ahead-of-time and just-in-time compilation comes down to the build time versus runtime problem. And my other favorite aphorism is that many software problems are actually distribution problems. Now that maybe is just from spending too much time at Anaconda, but I really do see a lot of cases software is hard because I have to give it to someone else and I want it to work for them. And so if I'm going to ship compiled software, you actually have to compile it, which means that as the builder of the software, I've locked in a bunch of choices. I've picked which Intel CPU I'm going to support. I had to compile without knowing what it was going to be used with. This library is considered an isolation from this other library, and Python is very modular, so we're often combining 3 or 4 libraries, but I have to compile them all separately. And so to mitigate that downside, you end up doing a lot of extra work. For example, we'll build bespoke dispatch systems in packages where you can get enough people and it's critical enough to do. For example, MKL has a dispatch system. NumPy now has a dispatch system. It has to build a lot of the ufuncs n times for different platforms, and internally we'll pick between them. But someone had to implement all of that. And once they've implemented, it's not immediately available for another tool. The other thing is, as mentioned in sort of the LPython talk, if you want to then be able to inline that functionality in a JIT, you'll have to implement it again. And so the number of times that advanced indexing has been implemented is probably at least 5, maybe 6. I lose track. Numba had to do it, LPython had to do it, SciPy had to do it. And so everyone is re-implementing the same algorithms over and over again in order to make them available to a higher level system. And then the final thing that has come up in discussions of things like now that Python 3.13 is getting sort of a very simple starter JIT is de-optimizing code. Taking code you went to the trouble to convert to C and converting it back up to Python so that it's available to a JIT. That seems like a lot of effort. And is there a way that we don't have to do that? And that seems kind of bonkers because then you are only going to be able to use that code fast with the JIT. You can't turn off the JIT anymore once you've de-optimized that code. So what we're trying to figure out is how we're going to distribute software for multiple CPU variants and without interfering with the possibility of JITs, but still acknowledging that sometimes you have to distribute compiled code. So that was the genesis of PIXIE when Stuart proposed it a couple years ago, is that it's really 3 related parts in this package. One, it's a storage convention for embedding metadata and multiple compiled function implementations into a single legal. It is a legitimate .so file. You can use normal tools with it. You can load it, all of those things. And so that allows us to put in extra information that can then be used by other tooling. So right now, for example, PIXIE will embed into the file function signatures and LLVM IR bit code, but it's totally generic. If there are other high-level things we want to put in for our tools, we can do that. And they all live in the SO file, and no one else has to be the wiser. As a convenience, by the way, PIXIE libraries are actually importable as extensions into Python for introspection. So you can just take the SO file and go load it and go rummage around on the contents and see whatever you want to see in the Python interpreter. That's just sort of a convenience. The second thing is inside of a PIXIE library is a trampoline that will pick, when you load the library, will pick the correct implementation. So if I, for example, have in there, I've built for SSE4 and AVX and AVX2 and AVX 512, I can have all of those implementations in that SO file, and when it loads, some code will intercept and load the correct implementation and make it available. And this all happens automatically. You do not need to have anything else available. It's just using features of the linker. So this was the real trick Stuart had figured out, was to make the linker do this without having to modify the linker. And then the last thing is tools for creating these libraries. The goal here is that you should be able to create this from basically anything, whether it's C or Python or Python or Fortran or Rust or whatever else you want. So we've currently implemented wrappers for C and Python, and then we actually have a Python API for directly programmatically controlling the build, which is actually what you'll see today, mostly because we want to control some options that aren't yet available in the wrappers, but will be very soon. So how PIXIE works is the source code that you're trying to compile comes in. Again, it may be very different languages potentially. And the PIXIE compiler will go take that, run it through the appropriate tool, whether it be Clang or something else, extract out the bit code, the unoptimized bit code, and then optimize it for the n different architectures that you would like to optimize for. Grab all of those artifacts and then jam them into the SO file along with the other boilerplate stuff required to make sure that when you load the SO file, you get some logic can check what CPU do you actually have and grab the version that's appropriate for your CPU. So ultimately, we want it to be this easy. We want to say, you have a library that's written in C, all you have to do is swap out your favorite compiler with PIXIE-CC, and it will produce an SO file. Same thing with Python. We just want to be able to make that swap super simple. If you actually take the PIXIE library and then go ahead and so let's say we have a library called objective function and import it. There's a special PIXIE attribute that's actually just a dictionary of arbitrary JSON data, so we can get out things like what were the architectures that were compiled into this thing, show me the LLVM bit code, maybe I want to go fish out the symbols, I can do all sorts of things like that. The one thing to note here is that the user does not need PIXIE at all. PIXIE is purely a build time tool. It is not a runtime tool. So you're not adding anything to your users or a dependency for your package other than for building. And if you, for example, have done this to a C function, you still have to figure out how to wrap the C function. It's not that PIXIE's not doing that part for you. So in the case of a thing that has a C func inside, you still have to build the C types wrapper or however you were going to call that C function. If you were going to use Python, this is obviously much easier. You can just call the function. But there's no sort of magic C wrapping going on here. That's sort of out of scope for this. So I was going to show you a couple demos. They're not too long. This one, hopefully this machine's still up. So because I do not have an Intel CPU here, I have to connect to one back at the data center. But let's say we were going to implement a, matrix vector multiplier or something like that in Python. So this is, again, totally normal Python code you might write. The programmatic API for using PIXIE kind of looks like this. It's a little bit verbose, but it's designed to give you a lot of control. Normally, we would want you to use PIXIE Pythonized to do this. Yep. Oh, bigger. I don't know how much bigger I can go with this thing. Let's see. Oop. Is that more readable? Cool. But what we need to be able to do is to specify a lot of these options in a config file, and so that's what's being worked on right now. But basically, if I just run this, this is taking a little while because it is compiling this file several times in order to, and running it through Python in order to generate the final file. So we just made BLAS kernels. Because this is, you can import these, it does actually require a specific build for a specific version of CPython. I think we could turn that off if we wanted, but if we want to then use it, here's an example of just some totally normal Python code that imports BLAS kernels uses it like any other Python function, nothing magic in here. And if I run it, it just tells me how fast it is, and that's great. This happened to use, I think, AVX 512, but I can force the dispatcher to pick a different version. And so in this case, I would want SSE2, super old. Maybe you have a really old computer. And you'll see the speed is actually about half the speed or something like that. So it's actually picking the different implementation. Now, normally this would automatically, you'd pick whatever it figured out was the default was for your computer, but you can force it for debugging purposes down. So that is, that's the dispatch mechanism. Second example, which is a little bit more crazy, and this was really the internal guiding example for us to really prove that we had mapped out all the parts here. So what this is going to entail is, I can run this in one locally because it doesn't depend on Intel. All right, so let's say we have a scenario. This is contrived, but it's designed to sort of touch all the parts. I have an objective function that I've written in Python. I've broken it up so I can keep the Python wrapper bit separate from the pure C bit, but that's a side issue. So I have an objective function here, and let's say I have the derivative of that. So that's written in Python. I have the derivative of that function written in C. Why not? Let's just switch languages. All right, so I've got a C function there. And then for bonus fun, I have decided to, so this could have been on the Play Nice track, decided to implement Newton-Raphson root solving in Python. And I am going to compile this using a, don't need to worry about it right now, but a sort of experimental Numba ahead of time compiler that's not really the subject of this talk. But let's just say I have a Python compiler that compiles ahead of time. So it produces an SO file just like this. So I've got an objective function in Python, a derivative in C, and the Newton-Raphson solvers in Python. So let me compile each of these things. Compile objective function. So that's going to go. There we go. You can see it compiled it 3 times because of that warning. Let's compile the derivative. And then let's compile this. All right. All right, so I've got 3 SO files here. And so what I am going to do is use them and use them 2 different ways. One way is I'm going to just use them as straight normal library functions. I would just call the function, I pass in a pointer to Newton-Raphson to call this function for your objective and call this other function for your derivative. The other thing I'm going to do then is call them in a way where Numba gets to use all the bit code from all of these files and re-JIT the whole thing together. And the nice part here is I, as the consumer of these libraries, can decide whether or not I want to do this. So if the application is one where I am willing to pay the JIT cost, then I can do that, but if I don't have to. And the packager doesn't care. So this is just going to run it a few different ways just to prove that it gets the same answer. So both the JIT and the ahead of time version get the same result, pi over 2. The JIT time speeds up by a factor of 5. We were actually curious how it pulled that off. And much to our surprise, apparently, LLVM is magic, LLVM was able to unroll Newton-Raphson, and because we were using those trig functions, work out that actually the answer is pi over 2, and compile the whole function down to return a constant. Occasionally, LLVM will do these things at compile time and scare us. The other favorite one I have is if you do, if you add up the consecutive integers, it will use the Gaussian formula and just make it a direct computation and get rid of the loop. So LLVM has these weird tricks involved, and you can finally use them if you can give it enough context so that it can see them. And so the only reason it was able to do that is because it could see the objective function, the derivative, and the Newton-Raphson solver all at the same time. But I shipped them all as ahead of time compiled SO files that you could have just used and ignored this capability entirely. So this was just what happened. Won't go through it again, although other than to say compilers are magic, we're occasionally surprised by the things that LLVM can do. So you can try these demos yourself. Again, probably the easiest way is just go to numba/PIXIE on GitHub. There's a SciPy 2024 directory that's got the example code and instructions on how to set up the environment. Right now, this is depending on unreleased versions of Numba and LLVM Lite that will be coming out soon. So what we did is made you a Docker image that just saves you the trouble of having to install those dev versions. So this will get easier over time. So there's a lot of next steps. This is very hot out of the oven. The number one priority for us is to simplify and refine this, get rid of the rough edges, make this easier to use. Again, our goal is that as a packager of C or Python code, this should be like a one-line change to your build script or something, and you don't have to worry about the details. You can decide maybe how many architectures you want to build for, and all the bit code gets embedded and you don't have to do anything. We obviously need more OS and hardware support. This is implemented for Mac ARM and Linux x86, maybe I guess Linux ARM as well, but Windows is obviously a requirement. So Stuart thinks he has an idea of how to do Windows. Wrappers for more languages, Fortran or Rust. I saw the LPython. I would love to jam this in LPython. I don't know where Andre went. There you are, yes. We should talk. Obviously cross-compilation support. Again, in a practical system you may need to build for a different CPU than you have. We should be able to build that in. Getting a little bit crazier, we would like to be able to consider maybe taking libraries built outside of PIXIE and maybe that you built in a couple different ways and fusing them externally rather than having to run them through the tool. An interesting one that, again, we asked the question, but we weren't sure if it was useful. Would anyone want to jam WebAssembly into here in addition to the bit code? Is that useful? I don't know. Let me know. And then definitely you might imagine if you have n versions of a library, they're probably pretty similar except for some chunks where maybe vector instructions or other things are being used. So you could imagine that there's probably some clever delta compression that you could do to keep these SO files from getting too bloated. That's something we haven't investigated, but we could definitely look at. And then there's just some quality of life tooling around making things like, PIXIE libraries that link to other libraries work okay. That I think actually was fixed very recently. PIXIE bin utils, again, these are legal SO files, so if you obj dump them, they look like normal libraries, but you don't get to see all the PIXIE information, and so we think that having sort of a variant of that is PIXIE aware would be useful. I think Stuart implemented this morning, so it's coming fast. So, to conclude, PIXIE is designed to enable ahead-of-time compilation without giving up hardware specialization and while supporting the runtime inlining capabilities of a JIT compiler. Ideally, we would like to see this used, obviously Numba needs this for itself. When we were conceiving of how our own ahead-of-time compiler would work, we wanted this capability so that the ahead-of-time compiler and the just-in-time compiler can work together. But we'd like to see other projects use it. My dream is that we can delete our implementation of advanced indexing and just use NumPys. That would be lovely. I don't know when that day will come, but that's the dream we have. And when you're thinking about this, think about in general, not just the specific, but the broader. We can embed arbitrary metadata, arbitrary IR, and pick between multiple library implementations at runtime. And imagine what you could do with that capability. You could ship a library that supports 2 different ABIs at the same time. You could ship a library that does other things depending on some hardware or system characteristic. And you don't have to worry about your packaging tools necessarily having to be aware of that, because that could get very long. So anyway, this is all very alpha, but evolving rapidly. Check out the code and demos on GitHub. We have documentation, so check that out if you'd like to learn a little bit more about how this works. The Numba discourse forum, we've created a category for PIXIE questions. That's where we'll post future announcements to. So if you want to follow the progress of this, jump in the forum and subscribe to it. And then finally, I wanted to some acknowledgments. This has required a tremendous amount of effort from the entire Numba team, while they are also firefighting things like LLVM and NumPy 2 and a lot of other stuff. So they're doing a lot of work just to keep Numba going while trying to do this really fundamental R&D on the side. And so I really want to recognize the team for that. Stuart, as I mentioned, is the main architect of PIXIE. I'm its biggest cheerleader, but I am not doing most of this development. And the other thing I wanted to call out is that the ideas that went into PIXIE are the result of a huge number of discussions with people like this. Numba users, people who don't use Numba, people who've never heard of Numba. And that all goes into our brain and slowly composts over time, and eventually we figure out how to do things. I looked back in my email. The first time we needed something like PIXIE was actually a discussion about JITs and NumPy from 2016 that Nathaniel Smith organized. We had this discussion in 2016, and we were like, I don't know how we're going to solve this. It took us 8 years, but we think we have a way to solve it now. So thank you, and I'll put back here for stuff. Questions?
Okay, thank you. And if you're online, please submit your questions to the Slack. We'll read them out loud, alternating with in-person people.
Thanks, Dan. One question/comment. At the very beginning, you made that great, hilarious, I'm laughing on the inside, joke about all software distribution, or many software problems are distribution problems.
Yep.
One of the things that you talk about this as an AOT JIT kind of an approach and whatnot for obviously optimization, but something else I think that maybe you can comment on it, but one of the things I recall is that we're surprised to find how many people have, like, as they do JITs and they start trying to ship Python production, they actually run into IT and production deployment sort of like barriers where you can't change the deployed artifact. Mm-hmm. Well, what if you want to distribute a bunch of dynamic stuff into that environment? And this actually gives you a chance, I think, right, to sort of have a more dynamic shipped artifact across a number of different kinds of hardware as your hardware backend sort of evolves over time. Yep. Can you speak to that a little bit? Or?
Yeah, I mean, this is sort of what I was getting at with the there are security considerations to pure just-in-time compilation. And so we would really like to support ahead-of-time compilation, but without having to make that hard switch at the beginning, that because I'm supporting ahead-of-time compilation, I give up any potential for JIT benefits in contexts where I don't need it. I shouldn't have to ship like the security hardened version of the package and the JIT version of the package. It should be the same package. And it's just as the consumer, I decide which of those situations am I comfortable with. That's really what we're trying to get to, is move the decision point from the builder to the consumer.
Okay, question about, is this in scope? To also include the code that would go to CUDA or
Mm-hmm.
ROCm, that sort of thing, in some high enough level way that it could be compiled for different versions of CUDA, so that as a distributor, mm-hmm. again, distributing software, a version of a package is not as dependent on the CUDA version. That's where you're distributing it to.
Yeah, I mean, actually, I will say, a lot of the inspiration for this also comes from how CUDA handles things, in terms of there's sort of that baseline PTX as well as kubins for all the different architectures. So yeah, if there is a thing you would stick in there, I mean, again, PTX might be the high level thing that you want to do, and so maybe this is already solved for CUDA. I don't know if there's an equivalent for ROCm or for other architectures. But yeah, again, we can, honestly, one of the things I'm interested in is possibly jamming MLIR in here so that you can be representing stuff at a high enough level that you could then lower to a wider range of accelerated backends. This is one of the reasons why just relying on the LTO that comes with the compiler isn't quite enough for us. We wanted the ability to pick the IR that goes in there, and maybe it's even higher level than LLVM at some point.
So I don't know if you've been following, but recently there's been a lot of discussion on PyPI about shipping variant wheels. Mm-hmm. So I noticed that you're like PIXIEs, you're planning to ship fat binaries. Mm-hmm. Have you thought about the binary artifact size problem and shipping binaries that only include code that will actually run on the CPU that it's being installed on?
Yeah. And we view this as sort of complementary to that, because again, Conda, you can do the same thing. You can have variants. There are situations where being able to, one of the things actually that isn't on the future list, is we actually wanted the ability to have tools that would let you thin a PIXIE library after the fact. So as a user in your Docker container, you're like, I am only going to use one of these things. And you could chuck them and get rid of the other variants. Or conversely, someone ships a PIXIE library and your computer didn't exist yet. And so I'm on some supercomputer or something, and so the person who shipped it made some choices about which architectures to optimize for, and you could be like, I want you to optimize for this exact one. Maybe you didn't have it. And so one thing we have talked about are the ability to re-optimize a PIXIE library after deployment or after it's been distributed, which again, is a capability that I think is complementary to the variant package approach.
Okay, so we have one more question. We've been going to the people who submitted online but are in person, so that's why we're walking up to random people. So John.
So this might be a naive question, but could you elaborate on where this logic happens for selecting the architecture that is currently in use if there aren't any runtime dependencies?
Yeah, there's a place, and this is where really Stuart would be helpful here. He's the one who figured this out. When LD is loading the library, there is a chance to intercept that load point and do something. And so there is a little tiny function there that basically says, okay, what is my criteria? In this case, I'm going to check CPU ID and look for what flags the CPU has. And there's sort of a function that's been pre-baked in there that's just the decision tree of, if I see this, then I'm going to unpack out of the SO file this particular version of the library and then go tell LD to load that thing out of memory. So it's a little bit, again, Stuart would do a better job explaining it, but that was the hard nut to crack, is he proposed this idea and then it took him like a year to realize how to make it work, because we wanted to not require replacing your linker or having PIXIE as some kind of runtime dependency.
Okay, let's thank our speaker one more time.